Hello everyone, and welcome back. Today we're going to continue our exploration of single variable calculus and continue our discussion in particular of differentiation and finding the derivatives of functions. So let's go over some of the basics that we discussed last time when we first introduced what a derivative was. So last time we defined the derivative of a function f at some arbitrary point x in the domain of f to be equal to the limit as some parameter epsilon approaches 0 of the difference quotient f of x plus epsilon minus f of x all divided by epsilon, which was just a limiting form of the average rate of change. And as also last time we mentioned, this is sometimes equivalently represented as f prime of x, or also described in terms of operations on functions, in particular the derivative of the function f of x, right? So this notation and that notation is practically the same. Here we're sort of implicitly, or not at least directly, mentioning that we're taking the derivative with respect to the x variable, since there's no other variables here, at least for the time being. So one of the main rules that we discussed last time was known as the sum and difference rule for differentiation. And it said that the derivative of the sum or difference of two functions f and g at some point x was equal to just the derivative of the individual functions at that particular point x, added or subtracted from each other, depending on what the sign was in the original. So this was referred to as the sum difference rule for derivatives. So in some sense, you can think of this as derivatives can distribute over addition and subtraction. Now, in terms of particular rules for particular functions, we discussed two main rules. In particular, the derivative of constant functions is equal to 0, provided that c is a real number, and of course you can extend that to the set of complex numbers if you want to. And two, the derivative of a monomial is going to be equal to a monomial of a degree 1 less than it was. And at least we proved that this is true for the set of natural numbers. And that's what we call the constant rule. So we have the constant rule, and we also have the power rule, which eventually we're going to extend to beyond the set of natural numbers, in particular to the set of real numbers, but we'll introduce that a little bit later. So let's work through just a couple basic examples just to make sure we understand these basic rules. So let's assume that somebody asks you, what is the derivative of the function minus 3x to the power of 4 minus 5x to the power of 3 minus 7 halves times x to the power of 2 minus 5 thirds times x plus e squared. Keep in mind e is just a number, therefore e squared is just a constant as well. So we already know that derivatives can distribute over each of these terms. So the derivative of minus 3x to the fourth is going to be equal to minus 12x to the power of 3 by the power rule. And then we're going to have the derivative of minus 5x cubed, so that's going to be minus 15 times x to the power of 2. And then 7 halves times 2, that's just going to be 7, so this is going to be 7 times x to the power of 1. And the derivative of a linear function is just the slope of that line, and the derivative of constants are just going to be equal to 0. Therefore, this expression is the derivative of that original fourth degree polynomial. Now, one can ask, is it possible that we can go backwards? And the answer is yes, as long as you're familiar with the functions that you're working with. So let's assume that somebody asks you, okay, the derivative of some unknown function, let's give it a name f, was equal to 8x cubed plus 5x squared minus 7x plus 8. What was that function equal to? So we know that when we differentiate polynomials of degree n, we always get another polynomial that is 1 degree less than it. So if we start off with a cubic polynomial and we want to find what function differentiates into this cubic, that means it must be a degree 4 polynomial, such that the derivative of that fourth degree polynomial gives us this 4 minus 1, or third degree polynomial. And in particular, when we take the derivative, we multiply the coefficients and the exponents and then subtract by 1. So if we want to go backwards, we're going to add 1 to that exponent and divide by that new exponent. So this function should be equal to what? So starting with the first, that's going to go up to a power of 4. And we're going to be dividing by that new exponent, so we're going to have 8 fourths x to the fourth. And obviously when you multiply or take the derivative of that term, you get 8x cubed back. Then the next term, that's going to go to x cubed, and we're going to be dividing by that new exponent. And then we're going to have x squared for the next term, so that's going to be 7 divided by 2. And then the what we call the antiderivative of a constant obviously is going to be a linear function. And keep in mind, there could have been a constant here, they could not have been. So since we do not know, we're just going to put an arbitrary constant and we're going to call it c there. So this is the general form for a function whose derivative is equal to that cubic. And here c is an arbitrary constant. So notice that this is not a particular function, but more so a family of fourth degree polynomials. It's not all of the fourth degree polynomials, it's just a particular subset of those fourth degree polynomials where they only differ by a particular constant c. So if this was one of those fourth degree polynomials, then this would be another, this would be another, and this would be another. So they're just a bunch of fourth degree polynomials that are sort of shifted up and down. And of course, they don't have to be anywhere. They could, cross the x-axis at the origin, perhaps. So those are just some of the basics of differentiation and derivatives of functions that we discussed up to this point. Now let us begin talking about other functions that we may want to find the derivatives of. One of the next basic functions that you probably should know the derivative of would be functions that are periodic, such as sine and cosine. So how would we begin to find the derivative of the function sine of x? So if we were to approach this via the limit definition, this would just be equal to the limit as epsilon approaches 0 of the function evaluated at x plus epsilon, so sine of x plus epsilon, minus the original function sine of x, all divided by epsilon. And of course, obviously, we would have to know some algebra in order to work that limit out. But let's think about this derivative a little bit before we actually get into the algebraic interpretation or evaluation of this derivative. So we already know that the function of sine x is going to have this type of shape where it's 0 at x is equal to 0, and then of course crosses 0 again at pi, crosses 0 over here at pi, and of course it has a local maximum at pi over 2 and a local minimum negative pi over 2, and it repeats every 2 pi units. So if we think about this from the derivative perspective, and we consider the line tangent to the curve at x is equal to 0, obviously the slope at x is equal to 0 is positive, right? So therefore we can say that, okay, the function sine of x is increasing when x is equal to 0, and since sine of x is increasing when x is equal to 0, that means the derivative of sine of x, which we don't know, is going to be positive when x is equal to 0. So the derivative could be equal to 3, it could be equal to 10, it could be equal to 1, it could be equal to a half, it could be equal to some positive number because the original function for which the derivative is associated is increasing, right? So if a function is increasing, that means the derivative is positive. Now if we look at another point, for example, let's go over here to x is equal to pi, and we consider the line tangent to the curve at that point, notice that the function sine of x is decreasing when x is equal to pi, and that means whatever the derivative of sine is, it's going to be negative when x is equal to pi, because the slope of the tangent line is going to be a negative number, at least from the graphical interpretations we should see that. And for example, if we look at x is equal to pi over 2, and also x is equal to minus pi over 2, then we clearly see that sine is neither decreasing or increasing at x is equal to 0. In particular, the slope of those lines is equal to 0, so obviously the tangent lines, so these two statements are together, of course, so the tangent lines are horizontal, which is always the case when you have a local minimum and a local maximum of a differentiable curve. That means the derivative, whatever it is, and that's of course going to be at x is equal to plus or minus pi over 2, not 0. So plus or minus pi over 2. Therefore, the derivative of the sine of x is going to be equal to 0 when x is equal to plus or minus pi divided by 2. right? So obviously there is a general statement that you could say about periodic functions, and that is if f is periodic, then the derivative of that function at an arbitrary point x will also be periodic. Right? Because if the y values and the x values are periodic with respect to each other, then they're going to be changing periodically as well, right? So what periodic function will be the derivative of the periodic function sine of x? Let's work through the algebra and see if we can figure out what it is. So again, the derivative of the sine of x is going to be equal to the limit as epsilon approaches 0 of the sine of x plus epsilon minus the sine of x all divided by epsilon. So what do we need to do here? So obviously we have the sum of the interior parameters of the function sine. So if you remember from fundamentals of mathematics, you should know that there's a sum identity for sine. And if you remember what that is, we can just use that directly. So that's going to be equal to the sine of x times the cosine of epsilon plus the sine of epsilon times the cosine of x. That's the sine of x plus epsilon, the sum identity for sine. And then we're going to have minus sine of x all divided by epsilon. So what I'm going to do here is just notice that this term here and this term here both have sine of x. So what I can do is I can factor sine of x out of each of those terms. So I'm going to have the limit as epsilon goes to 0 of the sine of x times the cosine of epsilon minus 1. And then we're going to have plus this last term, which is just going to be cosine of x times the sine of epsilon, just rewritten, all divided by epsilon. So now what I'm going to do is I'm going to split this fraction into two fractions, and I'm going to distribute the limits over those two fractions. So what is that going to give me? So this is going to give me the limits as epsilon approaches 0 of the sine of x times the cosine of epsilon minus 1 divided by epsilon, and then we're going to have plus the limits as epsilon approaches 0 of the cosine of x times the sine of epsilon, all divided by epsilon. So notice that these limits are with respect to epsilon. Therefore, everything that only has x in it and does not have an epsilon and is multiplied by the rest of the function is just a constant as far as my limits are concerned. So what I can do is I can factor those epsilon independent terms outside of the limit since they are just functions. So that's going to give me sine of x times the limit as epsilon approaches 0 of the cosine of epsilon minus 1 all divided by epsilon plus the cosine of x times the limit as epsilon approaches 0 of sine of epsilon divided by epsilon. So these limits here should look very familiar to you. We should know that this limit goes to 0 and this limit goes to 1. Those are our special limits. So that's going to give us the sine of x times 0 plus the cosine of x times 1, and therefore the sine of x times 0, that's just going to be equal to 0, and we're just going to be left with cosine of x. So therefore, the derivative of the sine function is the cosine function, right? And if we sort of look at the cosine function, notice that the value of this curve is equal to 1, right? So notice that this is the point 0, 1. That means in terms of our original function, sine, remember that the slope of that tangent line was positive, and we see that the slope is going to be equal to 1 from that particular cosine curve, right? Because the derivative of the sine curve when x is equal to 0 is just going to be equal to the cosine curve evaluated x is equal to 0, which is the cosine of 0, which we know is equal to 1, right? And obviously the derivative of this periodic function is indeed periodic, and indeed it is equal to the cosine function. Now that we know what the derivative of sine is, a natural question would be, well, what would the derivative of cosine be? So one could guess, well, the cosine function, we already actually know what that is. So obviously the derivative should be equal to 0 when x is equal to 0. It should be equal to a negative number when x is equal to pi over 2. It should be equal to 0 when x is equal to pi. It should be equal to a positive number when x is equal to 3 pi over 2, and it should repeat periodically, just like sine did. So let's see if we can sort of figure out exactly what is the derivative of cosine. So if we approach this again from the limit definition, we're going to have the limit as epsilon approaches 0 of the cosine of x plus epsilon minus the cosine of x all divided by epsilon. Just like the sine function has, this function cosine does have a sum angle identity, and that's going to be equal to the following in case you don't remember it. So it's going to be the cosine of x, cosine of epsilon, change the sign, so if it's plus, this is going to change to minus, and then it's going to be minus sine x sine epsilon, and then we're going to have a minus cosine x all divided by epsilon. Just like before, I'm going to group all of my terms that have my cosine x term, and then I'm going to leave that term alone, at least for now. And this is going to be equal to the limit as epsilon approaches 0 of the cosine of x times cosine of epsilon minus 1, all divided by, actually I'm not going to split it up quite yet, even though we're going to eventually. We're going to have sine of x times the sine of epsilon, all divided by epsilon. So I'm going to split this fraction into 2 over the course of this minus sign, and I'm going to factor out my cosine x and my sine x after I distribute my limit to both of these terms. So once I conduct that, that's going to give me the cosine of x times the limit as epsilon approaches 0 of the cosine of epsilon minus 1 divided by epsilon, and then we're going to have minus the sine of x times the limit as epsilon approaches 0 of the sine of epsilon divided by epsilon. So we know that this limit here is going to go to 0, and this limit here is going to go to 1. So this is going to come out to the cosine of x times 0 minus the sine of x times 1. So we're just going to be left with the negative of the sine of x. So we have the derivative of sine x is equal to the cosine of x, and now we have the derivative of cosine x is going to be equal to the opposite of sine of x, right? So it's not quite periodic in terms of differentiation in terms of cycles of 2, but it's almost sine, it's just its opposite. So, in case you aren't already aware, you can take the derivative of a function many, many times, right? For example, if I take the derivative of x to the power of 4, that's going to give me 4x cubed. But can I take the derivative of x to the power of 4? And indeed you can. This is usually what we refer to as the second derivative of that function. So that's obviously just going to be the derivative of 4x cubed, which would be equal to 12x squared. So we're going to go from a degree of 4 down to a degree 2 because we iterated this differentiation operator twice, right? So let's see if we can approach this on the sine and cosine functions. So we already know that the derivative of sine is equal to the cosine function. The second derivative of sine is just going to be the derivative of cosine, which is going to be equal to the minus sine function. If we consider the third derivative of sine, then that's just the derivative of the second derivative of sine, which is just going to be equal to minus sine, which we know is going to be minus cosine because that minus can sort of factor out of the derivative operator, and the derivative of sine is cosine. And the fourth derivative of sine is going to be equal to the derivative of the third derivative of sine, which we know to be equal to minus cosine of x, and we know the derivative of cosine is minus sine, and those two minuses are going to cancel, and that's going to give us back to where we started in terms of the derivative, or no derivatives at all, right? So obviously if we consider the fifth derivative of this function, the sine of x, that's going to be equal to the derivative of sine, but that's actually back to the first derivative of sine, right? So that's obviously going to be equal to cosine of x, and obviously you could recursively apply this as many times as you want. For example, let's assume that we're interested in, for example, the 17th derivative of sine. That's obviously going to be the same as the 17 minus 4th derivative of sine, so that's going to be equal to the 13th derivative. And that's obviously going to be the same as the 9th derivative of sine. That's obviously going to be equal to the 9 minus 4, which is 5th derivative of sine. And that's obviously going to be equal to the first derivative of sine, which is going to be equal to cosine from these observations that we have here. Therefore, the 17th derivative of sine is equal to cosine by that nice periodic pattern. The next basic function that we're going to consider taking the derivative of is the fundamental exponential function, the derivative of e to the x. So as usual, we're going to apply the limit definition to this function. So that's going to be e to the power of x plus epsilon minus the function itself, e to the x, all divided by epsilon. So this can be decomposed by the properties of exponents. So it's going to be the limit as epsilon approaches 0 of e to the x times e to the epsilon minus e to the x all divided by epsilon. Notice that I have an e to the x in both of these terms, and this limit depends on epsilon only, so I can factor that outside of my limit. So I'm just going to be left with the limit as epsilon goes to 0, and let's actually throw our e to the x on the outside, so e to the x times, and that's going to be left with e to the epsilon minus 1 divided by epsilon. Now this limit should also look familiar. We should know that that limit goes to 1, and therefore we're just left with e to the x. Now notice that the derivative of e to the x is itself. So if somebody asks, okay, well the derivative of some function f of x is equal to that particular function, what is that function equal to? You should say that that function is equal to e to the x, right? So the derivative of the exponential function is itself. So it's quite a very interesting property or property of derivatives, and there's actually a lot more to it than meets the eye, but we'll revisit the beauty and truly magical reason why this is a little bit later on. So, obviously, if we can take the derivative of the exponential function, we should be able to take the derivative of its inverse. So, what is the derivative of the natural log function equal to? So, again, if we apply the limit definition, this is going to be the limit as epsilon approaches 0 of the natural log of x plus epsilon. So, x plus epsilon minus the natural log of x all divided by epsilon. Now this one we're actually going to be using a little bit of algebra to work this out, so let's see if you can follow. So the first thing that I'm going to do is I'm going to use my properties of logarithms for this top term. So when you subtract two logarithms of the same base, you can divide their interiors. So we're going to have the limit as epsilon approaches 0, and I'm going to write this 1 divided by epsilon as just a fraction on its own. So I'm just going to write this as 1 divided by epsilon times the natural log of the first term divided by the second term, right? So that's what we get. And we can divide that x into the first and the second. So we're going to be left with the limit as epsilon approaches 0 of 1 divided by epsilon times the natural log of 1 plus, and we can write this as, for example, 1 divided by epsilon times x, and you'll see why I want to write this in just a moment. Now, I'm going to define a new variable here. I'm going to call this omega, and I'm going to call omega to be equal to 1 divided by epsilon. So omega is a function of epsilon, so what does it look like? So let this be the epsilon axis and this be the omega axis, so then we should know that this function looks like this, right? It's just y is equal to 1 over x, just with different variables. So notice that as epsilon gets close to 0, from the right-hand side, omega gets close to positive infinity, and as epsilon gets close to 0 from the left-hand side, omega gets close to minus infinity. So we can say that as epsilon goes to 0 from either side, then omega is going to be equal to plus or minus infinity, right? So we can say that. So what I'm going to do is I'm going to change this limit in terms of epsilon, or from epsilon in terms of omega, and everywhere I see 1 over epsilon, I'm going to be replacing that with omega. So this limit is equivalent to the limit as omega approaches plus or minus infinity of omega times the natural log of 1 plus 1 over omega x. Now I'm going to be bringing this omega up to the power of this little sum of rational functions, and that's going to give me the limit as omega approaches plus or minus infinity of the natural log of 1 plus 1 over omega x to the power of omega. Now we know that the limit of a composition of functions is equal to, as long as there's no variables that we're passing over in terms of omega, this limit can pass inside of this natural log. So we're just going to be left with the natural log of the limit as omega approaches plus or minus infinity of 1 plus, and let's actually rewrite this x on the top. Let's write that as x to the minus 1 divided by omega to the power of omega. So you should remember that the limit as x approaches plus or minus infinity of 1 plus a divided by x to the power of x, this is actually just equal to e to the power of a. Typically, if a is equal to 1, that's our baby limit that we memorized from before. That's just e to the 1 or just e. So using that property, we're just going to be left with the natural log of e to that constant, which is x to the minus 1. Natural log of e cancels, so we're just left with x to the minus 1, which is just 1 divided by x. So that means what? So let's sort of summarize this very interesting property. So that means that the derivative of the natural log of x is going to be equal to the function 1 over x, provided that x is bigger than 0. So this, of course, has a restricted domain because the actual function has a restricted domain, but you can actually extend this using absolute values, so the derivative of the natural log of the absolute value of x is just going to be 1 over x, provided that x is not equal to 0. So up to this point, we have derived and also proved these particular formulas for the derivatives of functions of a single variable. In particular, we have the sum and difference rule for derivatives, the derivatives of constants being 0, the derivatives of monomials, for which of course decrease by 1 degree and also change that leading coefficient, the derivative of sine being cosine, the derivative of cosine being minus sine, the derivative of e to the x being itself, and the derivative of the natural log function being the rational function 1 over x. So there's obviously several other functions that are missing from this list. For example, tangent, hyperbolic functions, other special functions, compositions, products, quotients, and so many other things, which we will definitely get to. But let's just take a look at this from the graphical perspective, because sometimes we might not know exactly what the algebraic representation of a function actually is. So for example, let's assume that I give you an arbitrary graph of a function, but I do not know what the algebraic representation of that function is. For example, let's assume that this is the graph of a function. It might look like a cubic, but it might be slightly skewed or slightly flat or fat or some, version of a cubic, I guess you could say. Right? So what would the graph of the derivative of this function look like, right? So we might not be able to tell you exactly what the function is, but we should at least be able to graph what that derivative may look like, right? So what does the derivative of this function look like? Okay, so let's actually give these points here because we have a local maximum at this point. So let's give that the x value a, and we have a local minimum there. So let's actually give that a name. Let's call that b. Because we know that the derivative at these points is going to be equal to 0 because that's going to be the slope of the tangent line at those points. So once we create our little graph here, so let this be x and let this be y, and let's put our points a and b on the graph, we know that this function is going to cross the x-axis at 0 because the slope of the original function is equal to 0 at those points. So if we choose a point to the left of A, notice that the tangent line is going to have a positive slope there. And if we choose a point on the right-hand side, notice that the slopes also are going to have a positive slope on that end. So that means the value of the derivative is going to be some positive curve on those intervals. And if we choose a point on the interior of A and B, for example, that point at the origin, notice that that slope is going to be negative, right? i.e. the function is decreasing on that interval. So the curve should be underneath the x-axis to some degree. So if this is f of x, that means this purple graph is the graph of f prime of x. So even if you don't know what the original function is, you can still find the graph of it, provided you have the graph of the original function. So let's just close this video out with just one more algebraic example of finding the derivatives, provided that you actually do have the function to find the derivative of. So let's assume that somebody asks you, what is the derivative of 5x cubed minus 2x minus 8 minus e to the x minus the sine of x plus the cosine of x minus the natural log of x? And let's do the absolute value so we can increase that domain. So we can of course distribute over sums and differences, so we're just going to be applying each of the rules in this expression. So the derivative of 5x cubed, that's going to be equal to 15x squared. The derivative of minus 2x will just be minus 2. And the derivative of minus 8 is just going to go to 0. The derivative of e to the x is going to be itself. The derivative of sine is going to be cosine. The derivative of cosine is going to be minus sine, and the derivative of minus natural log of x is going to be 1 over x. And obviously the domain of this function obviously is that x cannot be equal to 0, which is mandated by that natural log function. And if that natural log function did not have that absolute value of there, then the domain would be x is greater than 0 for the domain. So that's again some more fundamentals associated with derivative operators. In the upcoming videos, we're going to be deriving more properties so that you can do derivatives more broader and general functions in terms of products, quotients, compositions, and also how to approximate derivatives even if you don't want or don't know how to find the exact form of a derivative. So I hope to see you there, and I hope you enjoyed this video. Take care.